Hello everyone, welcome to AAT Tech Talk. My name is Narala Siddhartha. My roll number is 20951 A6744. My subject is Big Data and Analytics. So today I'm going to discuss about Big Data Analytics for electric vehicle integration in green smart cities. So let's start. The huge amount of data generated by devices, vehicles, buildings, the power grid, and many other connected things, coupled with increased rates of data transmission, constitute the big data challenge. Among many areas associated with the Internet of Things, smart grid and electric vehicles have their share of this challenge by being both producers and consumers, that is, prosumers of the big data. Electric vehicles can significantly help smart cities to become greener by reducing emissions of the transportation sector and play an important role in green smart cities. In this topic, we first survey the data analytics techniques used for handling the big data of smart grid and electric vehicles. The data generated by electric vehicles come from sources that vary from sensors to trip logs. Once this last vast amount of data are analyzed using big data techniques, they can be used to develop policies for sitting charging stations, developing smart charging algorithms, solving energy efficient issues, evaluating the capacity of power distribution systems to handle extra charging loads, and finally determining the market value for the services provided by electric vehicles, that is vehicle to grid opportunities. This topic provides a comprehensive overview of the data analytics landscape on the electric vehicle integration to green smart cities. It serves as a roadmap to the future data analytics needs and solutions for electric vehicle integration to smart cities. According to International Data Corporation (IDC), vis- visionary presentation on the digital universe of opportunities, the overall created and copied data volume worldwide was 4.4 zettabytes in 2013. The volume of data is doubling every 2 years, and by 2020, the total volume will exceed by 44 zettabytes, that is, the 44 trillion gigabytes. Besides the volume, the velocity of the data is growing as a result of the advances in communication technologies and the Internet of Things. Such numerous data sets with high velocity, veracity, and variety are expressed as the big data phenomenon. Smart grid and electric vehicles are among the main drivers of IoT as they form a large connected network of things such as vehicles, charging stations, smart meters, intelligent electronic devices, IEDs, and phasor measurement units PMUs. They are also anticipated to the drivers of green smart cities by enabling efficient integration of renewable energy and lower emissions. The green smart city vision anticipates almost all flat surfaces, including roads, covered by solar panels to maximize the utilization of solar energy. EVs carry dozens of sensors that provide data, including user driving behaviors, battery security via a battery management system, and grid charge management via charging stations. Drivers as well carry smart devices and variables that contribute to the data generated on roads. With smart autonomous self-driving cars, those data will be continuously moving from cars to servers and cars to cars. In the case of EV grid integration (EVGI), their charging and discharging patterns is tightly coupled with the operation, security, and efficiency of the smart grid. In that sense, data analytics play a crucial role in EVGI, green smart cities, and other green infrastructure as presented. In particular, charging planning and harmonization of EVs for selling power back to the grid require fast and reliable data analytics techniques. In this topic, we provide a comprehensive survey of existing techniques and provide a roadmap for future technologies in data analytics for EVGA applications in green smart cities. We start with a brief overview of smart grid and EVs to present the applications, and potential challenges. We discuss the source of big data generation in detail. Then we continue with a survey on data analytics tools that are used in this domain. The article aims to introduce the existing data analytics studies on EVs and smart grid. Hadoop based cloud platforms, prediction methods, and decision support tools are among the super surveyed data analytics studies. The article provides a requirement analysis for future data analytics tools and aims to serve as a roadmap for researchers in this area. Okay, an overview of EV integration with V2G, G2V, power and information exchange, heterogeneous communication technologies, data flow, cloud integration, applications, and big data analytic tools. As shown in the figure, EV-EVSC grid communication can be implemented by power line communication and wireless networks. Note that EVSC is the EV support equipment and is used interchangeably throughout this topic. EVs can be charged, and the big data from EVs and all other entities are stored and processed over the cloud for various application purposes, including optimization, charging. Some widely used big data tools are also plotted in the figure. The rest of the article is organized as follows. The following section provides an overview of the integration of EVs. Smart grid is the modernized electrical grid that integrates advanced sensing, communication, and control functionality for the purpose of enhanced efficiency, reliability, and security in the operation of the utility grid. EVs are either completely or partially powered by their onboard batteries, which are charged by the power grid. Plug-in EVs use less fossil fuels and emit much less CO2 compared to conventional vehicles, and therefore are incentivized by many governments to improve air quality and reduce greenhouse gas emissions. Despite the advantages, there are still challenges for the widespread adoption of EVs. Limited driving range and associated driver range anxiety, long duration for charging, and non ubiquity of charging stations are the critical barriers to the penetration of EVs. In addition, with a growing EV market, the impact of EVs on the power grid is a matter of concern, especially at the distribution level. This may result in adverse effects such as peak loading, increased losses, voltage unbalance deviations, and need for additional network reinforcement. Data management in EVGI plays a vital role for healthy integration of these new technology vehicles into the future green smart cities. EV batteries are charged using onboard chargers and EVSC, also known as charging stations. EVSCs can be located at residential premises, parking lots of commercial buildings, and any roadside charging facility. The EV integration framework enables EVs to be controlled by the smart grid or aggregators via the communication between vehicles and the grid. Communication between EVs and the smart grid can be a mix of wireless and wired technologies, including PLC, ZigBee, Wi-Fi, LTE, and fifth generation 5G wireless networks. A description of a hard description of EV grid interaction and the EV GI system with bidirectional power and communication architecture are shown. The communication between an EV and the smart grid includes two concepts: basic signaling and high level communication. A hardware description of EV grid interaction and EVGI system, the bidirectional power and communication architecture are shown. The communication between an EV, the basic signaling refers to EV charging control methods utilizing the control pilot signal of the charging plug for basic G2V charging control as shown. This control is realized by modifying the duty cycle ratio of the control pilot signal, which is already available in all of the plug-in EVs in the market. Communication functions via the current control pilot pin has a fairly simple structure and cannot provide the bidirectional information required between EV and grid. On the other hand, V2G control is achieved via high-level communication that uses PLC superimposed on the control pilot signal. In the case of PLC, V2G communication is overseen by EV communication controllers. Furthermore, the analyzed data has not been transformed into decision making in many of the studies. The value of big data analytics tools would be better evaluated as they transmission into decisions for system operations. Nevertheless, there are many future opportunities to explore in this area. In the following subsection, we focus on various applications in the EV and smart grid domain that can benefit from big data analytics. Thank you.